Now we're going to be looking at a hydrogenation reaction. And we can really start this with a discussion of fats and oils because this ties into the reaction we're going to be talking about. So here I have an infographic from Compound Interest that's useful for this discussion. So right here, this is the structure of a triglyceride. And when somebody says a fat or an oil, this is really what you're referring to, is this triglyceride. Now, in this case, the one that's shown here is completely saturated, meaning there's no double bonds in the structure. When somebody talks about an unsaturated fat, that means there's double bonds in the structure. Now, these structures shown over here to the right are basically what happens if these ester groups get cleaved in the fat. You end up with these fatty acid structures. And these are also part of the fats that we talk about. So now you can see some of the differences where, when it's saturated, there's no double bonds in the structure. You can have monounsaturated, which means there's one double bond in the structure. Polyunsaturated, meaning there's multiple double bonds in the structure. And then when you hear the term trans fats, that just means you have a trans double bond, which is what we have here. It is thought that cis double bonds in fats are healthier than the trans double bonds in fats. So tying this into hydrogenation, maybe you've heard the term partially hydrogenated fats or oils. What that generally means is you started out with a fat that had several double bonds within it, primarily cis double bonds or cis alkenes, and it was subjected to a hydrogenation, meaning the double bonds were reacted with hydrogen gas to reduce them to single bonds. But if it's partially hydrogenated, that means all of the double bonds weren't reduced. And in general, what's left behind are trans double bonds, which are unhealthy. So that's why there's kind of a negative connotation associated with partially hydrogenated fats and oils. In a hydrogenation reaction, we're starting with an alkene and subjecting it to hydrogen gas. So in the same way Cl2 adds a chlorine and chlorine across the double bond, H2 will add H and H across the double bond. So what I'll do is draw my starting material without the double bond. It still has the two original hydrogen, and we've added now a new hydrogen on each carbon. But as it's written, this reaction is never going to take place in our lifetime. The activation energy is just too high. So what we have to do is add a metal catalyst to this. Common metals include this Pd/C, that is palladium on carbon. It's basically palladium metal dispersed over charcoal. Platinum, nickel, there's others. These are probably the three most common. Having one of these metal catalysts is necessary for the reaction to occur at a useful rate. So in terms of kind of how we can see this on a reaction diagram, and I'm not including all of the intermediates involved here when the catalyst is used, but we have the starting material and the product, and the product will be a bit lower in energy than the starting material. But for the uncatalyzed reaction, you're looking at a really high energy barrier. And what that means, it's just very hard to surmount, even with heating and things like that. So what the catalyst does, we retain the starting material in the product, but it lowers this energy barrier to a much more reasonable activation energy. And in the catalyzed reaction, the metal does get involved in the mechanism, but at the end of the reaction, it comes back out unchanged. So you only need a tiny quantity of it to make the reaction go. So let's look at the mechanism for this. And I'll preface this by saying that transition metal catalyzed mechanisms are quite a bit different than what we typically see with electron pushing. And the reason for that is because now we're not necessarily dealing with a typical nucleophile and electrophile. The metal incorporates its own special chemistry into the reaction, but we can still understand what's going on. So basically what's going to happen is we take the hydrogen gas, and that will interact with the palladium metal, or whatever metal you use. And the palladium actually inserts itself between the hydrogen-hydrogen bond. So we end up with the palladium having two hydrogens on it. Next, the alkene comes in close proximity to the palladium. And what it does is it coordinates with the metal. So we get something that looks kind of like this. So coordination is just kind of a partial bond between the pi bond of the alkene and the palladium. From there, we get the hydrogenation step, where the hydrogen's added. So you can kind of think of this like the pi bond taking a hydrogen, sending those electrons to the palladium, and then the palladium spitting out the other hydride to go to the double bond. In the end, we end up adding both hydrogen to the double bond. So we get our product plus the catalyst regenerated. And what you can see here, and this is going to become important when we discuss stereochemistry, is that because these hydrogens are both attached to the palladium, they're coming in from the same side, they add from the same side. It's a syn addition. Let's look at a few important features of the hydrogenation. The first is one that we discussed. Hydrogen adds syn across the double bond. So that means if we take this alkene here, I'll add hydrogen, and I'll use platinum as my catalyst. Both hydrogen will add either from the front or the back. So we can end up with, if it adds from the front, we'll put the hydrogens on wedges, and those methyl groups will be dashes. If it adds from the back, I'll put the hydrogens on dashes, and the methyl groups on wedges. Now in this case, those happen to be completely identical, because if you flip this over, you get the other molecule. Now, what we often do is we often write this without even drawing in the hydrogen. We'll write them implied. So it's just as valid to draw this structure like that and have those hydrogens implied. The second feature has to do with reaction rate. The reaction rate of hydrogenation decreases with alkene substitution. So for example, if you have a monosubstituted alkene versus a trisubstituted alkene, if we subject both of these to hydrogenation, the tri-substituted alkene will react more slowly. And that just has to do with the metal coordinating to the palladium catalyst for that hydrogenation step. When there's more things around the alkene, it makes it difficult or more difficult for it to get into close proximity with the metal. As opposed to less substitution, this more easily coordinates to the metal. The third feature that I sort of alluded to before earlier is that the hydrogen will add from both the front and back faces of the alkene, and that can result in stereoisomers. Let's look at an example of this. Here we're starting with this alkene, but we already have one chiral center, and that one is not going to get affected. And we're adding H2 and palladium on carbon. And of course, this hydrogen can add from the front or the back. So if we add it from the front side, then both hydrogen will be on wedges. So let's draw our molecule. Again, leave everything the same, except the 2 carbons where the reaction is taking place. So if the hydrogen comes in from the front, it will be on a wedge here and a wedge here. And then the ethyl group will end up going back because we already have 2 bonds in the plane, 1 wedge, the other must be back. Now, in this case, we have our original chiral center. We formed a new chiral center. When I drew this product, I put this hydrogen kind of on a wedge for emphasis, but we generally don't want to put dashes and wedges at carbons that aren't any type of 3D center. So I'm going to clean this structure up a bit by making the hydrogen implied. And in fact, I'm going to imply both hydrogens. So I'll put the methyl here that we already had. And then on the next carbon over, we have the back ethyl group. That's our new chiral center. And it was directed by the addition of the hydrogen. Our other product will have the hydrogen coming in from the back. So we do it basically the same way. Leave your first chiral center as is. And then if the hydrogen comes in from the back, we have a back H here, a back H here, and then that pushes this ethyl group to the front. And there's our new chiral center. Again, let's clean this up and make the hydrogen implied. And we get this product with the 2 chiral centers. These two, because we have one chiral center that stayed the same, one that is inverted, this is a pair of diastereomers.